Okay, in experiments 1 and 2, the first 2 weeks of lab, you're going to be learning how to determine physical properties of organic molecules and also using those physical properties to identify an unknown. And you're going to do both experiments in the first 2 weeks. Half of you will do experiment 1 the first week and then do experiment 2 the second week and vice versa. So in experiment 2, what you're going to do is we're going to learn how to measure boiling points, measure the density, and refractive index of organic molecules. And then we're going to use those 3 physical properties to identify the identity of an unknown liquid that you're going to be given. So organic liquids have a number of physical properties that can be used to determine its identity, and to be honest, it's mostly to narrow down the possibilities. If there's 9+ million organic molecules, then these 3 physical properties we're going to measure today will probably narrow a list down to maybe, 100, which is better than 9 million. So in this experiment, what we're going to do is we're going to learn how to, first of all, set up a macro scale simple distillation apparatus, which you're going to do over the course of the year. You're going to be you're going to do simple distillation, so we're going to learn how to set up the apparatus. Then we're going to perform a simple distillation that is typically used to purify a liquid. But in this case, we're going to use the simple distillation to determine the boiling point of an unknown liquid. Then we're going to measure the density of that unknown liquid and its refractive index. And then using those 3 physical properties, you're going to determine the identity of an unknown liquid given a list of potential possibilities. So boiling points of organic molecules in general chemistry, basically the Chang definition of boiling point is that the normal boiling point is the temperature where the vapor pressure of a liquid equals 1 atmosphere pressure. We all know what boiling looks like, but that's the technical definition from general chemistry. Now, one thing we should notice here is that we have a normal boiling point and it's 1 atmosphere pressure. If you lower the atmospheric pressure on a liquid, you can get it to boil at a lower temperature. If you raise the pressure on a liquid, you can get it to boil at a higher temperature. The higher temperatures, actually, that's what you do when you steam pressure cooker. You're raising the temperature of the water that's cooking your food to above 100 degrees Celsius. That's what you do to sterilize something. When we haven't talked in general chemistry, we don't talk much about lowering the atmospheric pressure, but in experiment 5, when we have our first encounter with the rotary evaporators, we'll actually see that when you lower the atmospheric pressure, you lower the boiling point. So it's possible to get water to boil at room temperature if you lower the atmospheric pressure enough. Basically apply a vacuum. Now, in melting point that you either have done or will do, changing the atmospheric pressure has a very little effect on the melting point, but it has a huge effect on the boiling point. So today we're going to measure normal boiling points at approximately 1 atmosphere of pressure. And the way that we're going to determine the boiling point is to perform what's called a simple distillation. And a simple distillation is a way to purify a liquid. And the way that this works is that we set up a simple distillation apparatus, and there's a separate video where I take you step by step through setting up the simple distillation apparatus. And in the lab, you'll go through this. The TAs or I will demonstrate, and you'll watch how we do that. But there is a separate videotape on this. And so here's, for instance, a simple distillation apparatus. We have a round bottom flask that'll contain our impure liquid. We have what's called a distillation adapter and a thermometer. We have the condenser, and then we have this thing called a vacuum adapter, which basically directs the liquid to drip out into a receiving flask, or in this case, a receiving graduated cylinder. So what happens is when you heat the liquid to boiling, the vapors form and the vapors travel up the distillation head. The vapors completely condense over the thermometer bulb so that we know the temperature of those vapors. The vapors will then turn and go into a condenser. In the condenser, you have water flowing through it, cold water that condenses the vapor into liquid. The liquid then flows down, drips out, and what we collect over here is purified liquid. Now, what we're going to be doing in this experiment is we're going to be measuring the temperature of the vapor to get the boiling point. Now, the boiling point sometimes is a single number, sometimes it's a range. What we're going to do is you're going to measure the three temperatures that you get on the thermometer when a quarter, a half, and 3/4 of the liquid has distilled over, and you're just going to estimate that. And so those three temperatures should be pretty close. If they're a range, they might be 1 to 2 degrees Celsius at the maximum. So that's how we're going to measure the boiling point. And later on experiments, we're going to be using distillation in order to purify liquids. So the first thing you'll do in the lab is you'll set up the simple distillation apparatus. And there's a video, as I said, that will take you through that. After you've assembled the apparatus, you're going to be given, and you're going to assemble the apparatus empty. You'll then be given a test tube that has an unknown organic liquid. First thing you want to do is write down the number in your notebook. If we don't know what number it is, we can't compare it and determine whether you have the unknown correct or not. So you got to write down the number in your notebook. If you don't do that and you don't show us a number, then you get 0 points for the lab. So you got to make sure you write this down first. Then what you're going to do is you're going to put the liquid into the round bottom flask. The round bottom flask should have boiling stones, and I go through that in the other video. Then we're going to heat the round bottom flask, and in this case we're going to use a hot water bath. So you should be able to guesstimate what temperatures or temperature range your liquids are going to boil at. Okay, here's the hint. If you say that your liquid boiled at 150 degrees, you might want to think about that. So we're going to heat the round bottom flask in the hot water bath, and then after a certain time period, you're going to see the liquid boil. You're going to see the vapors rise up the distillation head and eventually fill it, be condensed, and then start dripping out into the graduated cylinder receiver. You're going to measure the temperature after 1/4, 1/2, and 3/4 of the liquid's been distilled, and that should give you a fairly small range of boiling point to work with. Okay. And then one thing you want to watch out for is after 3/4 of the liquid is distilled, you want to turn the hot plate off. In general, we never distill the round bottom flask to dryness. I think there's a pre-lab question or post-lab question on that you can find out the reason for that from your lab textbook. But let's just say bad things happen in general when you boil stuff to dryness. So that's one physical property of our liquid. The next thing we're going to do is measure the density, and then we're going to use then we're going to determine refractive index. In this case, you're going to use the purified distilled liquid to measure density and refractive index. So measuring the density, this isn't that hard. The density of a liquid is measured in grams per milliliter. It is a fundamental property, and some things that you're going to learn over the course of the semester are that the density of water is approximately a gram per mil. You probably learned that in general chemistry. For organic molecules, though, there's actually a distinction in densities. In general, if you have a non-halogenated organic molecule, and that's one that contains only carbon, hydrogen, oxygen, nitrogen, but no chlorine, bromine, iodine, or fluorine. And fluorine's questionable. But if you have a non-halogenated organic liquid, their densities tend to be less than a gram per mil, which means that they float. They'll have a density less than water. And so an example of that would be, you've all seen oil floating on water. Oil is a non halogenated organic liquid. If you have halogenated organic liquids, though, things that contain chlorine or bromine or iodine, then in general those have densities that are greater than a gram per mil, which means that they'll sink in water. And so if we mix a chlorinated organic material in water, we'll actually end up getting two layers, and the bottom layer will typically be the chlorinated organic because it has a density less than 1. I'll point this out to you when we get to doing separations in some of the later experiments. But the density is an important factor, and these are the two general rules. So measuring the density, you're going to get a volumetric pipette, one like you used in general chemistry. There's a pipette bulb that goes with it, a propipetter actually. You're going to measure you're going to get a sample vial with a cap, measure the mass of the sample vial with the cap, pipette in 1 milliliter of liquid, reweigh, and then the mass of liquid you added is divided by 1 milliliter, and you get the density of the organic molecule. You're going to do this procedure twice so that you get two measurements. And what you can do is just simply take the measurement after 1 milliliter, take that mass, pipette in a 2nd milliliter, and measure the mass again. If your two densities are very similar, and let's say within 10%, then you don't have to do a third trial. If your densities are different, then you're going to have to do a third trial. So then you're going to calculate the average density of the unknown liquid. So that's a physical property that we're going to use along with boiling point. And then finally, the third, and this just outlines that procedure again, the third physical property that we're going to learn about is refractive index. Now, the refractive index is technically the ratio of the speed of light of the sample in a vacuum relative to its speed of light through the substance. We use what's called an Abbe Refractometer to measure the refractive index. And your lab book goes into the equations, but basically when a beam of light hits a substance, it bends. Okay, that's a refractive index. So the refractometers can give us the refractive index, which is called n sub d20. And it'll give us that refractive index to 4 decimal points, which is pretty high precision. Just for reference, the n is the refractive index, the 20 is the degrees of the measurement, and d is a very specific wavelength of light that's used, which is called the d wavelength of sodium. And the d wavelength of sodium is one of the wavelengths that a sodium emission lamp gives off. So one of the things we have to worry about is the refractive index does change with temperature. On the Abbe Refractometer, you will see that there is a thermometer that you can record the temperature, and you're going to want to make sure you write down the temperature because I doubt it's going to be exactly 20 degrees. The literature values that you find in most of the references are corrected to 20 degrees. So to correct a refractive index measurement to 20 degrees, you use this equation where you take your refractive index at that temperature and then add to it 0.00045 times the number of degrees you're away from 20 degrees. So once you measure the temperature of the sample, you're going to have to correct that back to 20 degrees for your samples because that's what the literature values that I've given you are listed at. We'll go through the procedure on how to do refractive index with you, but just as an outline, you can use this as a reference. This prism actually opens, and that's where we put our sample to make our refractive index. So the first things you always do is you clean the prism, and there's an upper part and a lower part. So you clean both of those using ethanol. There's a bottle of ethanol and a plastic pipette. Wipe it down with the Kim wipe, and you always clean the prism unless you've seen somebody else clean it in front of you. Always assume the prism's dirty and needs to be cleaned. So we clean it with ethanol, we dry it off, and then you're going to take a plastic pipette. You have to use a plastic pipette, not a glass pipette, or else you'll chip the quartz crystal that's used as this in the refractometer. Take a plastic pipette and fill this area with liquid. Usually takes 1 to 2 milliliters. So you're going to place that on the clean surface and then take this door and close it, and now you're ready to make the measurement. So the sample prep is very easy. You turn the instrument on by flipping the switch on the left hand side down to the horizontal position. The light will come on. You position the light so it's shining right on this slit on the refractometer, and that you might have to play around with the position of the light in order to get the sharpest image possible. So once you do that, then you look through the eyepiece, and what you're trying to do is to get an image that looks like this. You've got a light half and a dark half, and then a line between them. So if you position the light, if you change the position of the light, you can get these to be greater or less in intensity. This line will move up and down between the light and the dark halves depending on the refractive index of the sample. To make the line move up and down, you use knob A. And to sharpen the interface between the light and the dark halves, you basically use knob B. The ultimate goal here is to get a sharp line between the interface and get that sharp line placed right on that center of that X. Okay, and this takes a little bit of practice, but usually once you find the light and the dark halves and you sharpen it up, then it's just simply a question of using knob A to put it right on the X. Okay, so that's our goal. Notice that this one, not very sharp, not on the X. You can do better. So once you've got this set up, then you're ready to make the measurement. So to read the refractive index, what you do is hold down this switch, and when you do, the light goes off and a light on the inside comes, so that when you look through the eyepiece, you'll see the refractive index, you'll see this line, and then you've got to measure the refractive index using this scale. It was incredibly hard to get pictures inside of this, so this was the best I can do. You'll see something that looks like this. You should be able to measure the refractive index to the 4th decimal point. Okay, so since I couldn't get a good picture of this, here's what you would typically see. So what is the reading of the sample above to 4 decimal points? Okay, and if you want to check yourself, take a minute, stop the tape, and see what you read. Because you might have to do that in the pre-lab quiz. Okay, got it? Well, how do we make this measurement? Well, we look and we see that the difference is 1.360 to 1.370. There are 10 graduations here. This is the 5. So at the dead center here, what you have is 1.365. Okay, that's this graduation. So that means that each one of these graduations is worth 0.001, and then inside of here, where you have to estimate, you're going to estimate it to the 0.004th decimal point. Okay, so if we do that here, we know that this sample has a measurement of 1.365, and between here and here then is 10 units. So I would say that the measurement here is 1.365, and I would call it 3, but I'd give you anywhere from 1.3652 to 1.3654. Okay, so that's how you would make the measurement. All right, you want to try another one? Here, let me take this line and not drawing it very straight. What would be right there? That measurement. Okay, stop the tape, make your measurement. Okay, you're back. This I would call right here where it crosses, I would call that 1.36. There's 5, 6, 7, 8. So 1.368. And I would say that I would call it 1.3688, 1.3689, somewhere in that neighborhood. Okay? So you have to learn how to read the vernier scale in order to make that measurement. Right? And like I said, might have to do this in a pre-lab quiz. You never know. Okay, so once you have been shown the procedure on how to make the refractive index measurement, probably the best thing to do is to measure the refractive index of a known material so that you can not only calibrate the instrument, but calibrate how good you are at it. So what I suggest is take some distilled water and make the measurement. The literature refractive index of water should be 1.330. I know that's not the 4 decimal points, but see how I think it's 1.3300 at 20 degrees Celsius. So make your measurement. If you have to correct it, you can correct it back to 20 degrees. Now, the idea here is that you can get a general idea as to how close the refractometers are to being properly calibrated. If they're not properly calibrated, they're a pain to do that. And so, for instance, if you get a number that's always 0.001 lower than it should be, then just keep that in mind when you measure the refractive index of your sample. Take your unknown, measure the refractive index, measure the temperature, correct your refractive index back to 20 degrees. Okay, so what we've now done is we've measured the boiling point, the density, and the refractive index. So we got 3 pieces of physical property to make the identification of the unknowns. So here's a partial list of unknowns from your handout. Let's say that I got a boiling point of, I don't know, let's call it 60 degrees. And let's say I got a density of, I don't know, how about 0.82, 0.81 grams per mil. And I get a refractive index corrected back to 20 degrees of something like 1.3100. Okay. Hopefully these work out because I'm just making them up. All right. The procedure says to identify the unknown by using the boiling point and then using a combination of refractive index. The least accurate of these physical properties is the boiling point. So what we're going to do is we're going to take our boiling point and I'm going to come up with a range of plus or minus 10 degrees on that in order to narrow down my list. So if I'm looking at 60 degrees, I'd be looking at something from 50, you know what, I'm going to take 49 and I'm going to go all the way up to 70 degrees, and for the sake of argument I'm going to count 72. So here's my list of potential unknowns. Okay, we're using a big range because the boiling point is not necessarily, it is not the most accurate, but what we want to do is to get a big enough range so that the density and density and refractive index will then give us the unknown. Now what you should do is once you've come up with your list of potential unknowns, you want to take your unknown number and your list to the TA, and they'll make sure that the unknown that your unknown is somewhere in this region. If it's not, they might say, well, you want to go a little higher or a little lower. Okay? But we're using a big range to give us a large possibility. So the next thing I'd do then is I'd use a combination of density and refractive index. And in theory, the refractive index is the most accurate measurement. Particularly if you have a liquid that evaporates very quickly, your density may not be perfect. So if I'm looking for something with a density of 0.81 and a refractive index of 1.31, I probably, the way I would do this is I would look at density. So I'm going to say, well, let's see, here on my list, this is pretty close. This one's pretty close. That one's kind of far away. That's kind of far away. So if it's me, I'm looking at these two as my two possibilities. And so looking at the refractive index, I would most likely say that my potential unknown here is the methanol, just given this set of data. Okay. Now it's possible that you may not be able to narrow down the unknown to two. You may, or to one. You may have two compounds that are very, very, very similar in density and refractive index. And in that case, it's perfectly acceptable to say these are very close, and so it's either this or this. Okay, but that's how we're going to make the identification. And so what you're going to do then is you're going to fill out the lab report form that goes with experiment 2. There's a copy in the handout. There's one on the Blackboard website so that you can print it out. You can hand write the answers into that lab report form, and then you're going to turn that in as your experiment report for number 2. There's no electronic copy that's necessary, so you can hand write it. If you're overly ambitious, you can also type it out. It doesn't matter to me. But you won't submit an electronic copy of experiment 1 or experiment 2. Okay. Right. So that's what we're doing in experiment 2, is to determine the identity of the liquid using boiling point with simple distillation, the refractive index, and the density. And when we make liquids in organic over the course of the year, we're going to use the boiling point and the refractive index as a qualitative test of purity. And so measuring the refractive index and the boiling point is going to give us two physical properties that we can use to assess the purity of our liquid.